this is the thing. Like we think about this. We think about this a lot. We think about the plant part a lot, but the rock part is actually really interesting. I have a hard time saying really interesting because it's literally, okay, this is how interesting it is. When here's a raindrop. Here's a raindrop. And in that raindrop, carbon dioxide can go in. Carbon dioxide dissolves really easily in water in real time. While a raindrop's falling through the sky, carbon dioxide is dissolving into it. And it changes the pH to about 5.6, I think. And because the reason it changes the pH, what does pH measure? Acid, base, right? And is this an acid or a base?
Acid.
It's a slight acid, right? Neutral is 7, water normally is 7 pH, and so 5.6 is lower, it's a little bit of an acid. And that's because H2O plus CO2 gives us H2CO3, which is carbonic acid. And interestingly, you're going to learn a little bit more chemistry today. So that carbonic acid, I'm going to erase this, put it up here. pH 5.6. Those are rocks. And so, what's that?
Okay.
You can take my word for it. It's rocks, okay? And if those certain kinds of rocks, for example, silicate rocks, C-I-S-I-C, oh God, what is it? Yes, CiSiO3. Calcium silicate rocks, very, very common. Silicon is actually, I think, the most common element in the Earth's crust. I might totally be wrong about that. It's a very common element in the Earth's crust. But when carbonic acid in the form of this raindrop falls on the land, the rain falls on the land, a chemical reaction happens. And it actually takes that carbon dioxide out of the air effectively, because what it does is it creates calcium carbonate plus. Yeah.
I was writing while you wrote the first line. Do you mind re-explaining that? The H2CO3.
Yeah. So this is right. This is the carbonic acid from the rain. This is not the same thing as acid rain, by the way, which comes from coal and sulfuric acid. This is just rain that is slightly acidic because of carbonic acid, carbon dioxide in the atmosphere. And so rain plus silicate rock makes calcium carbonate and sand, right? SiO2. Silicon dioxide is sand. It's what we make glass out of. It's sand. You're familiar with sand. It's out there. And calcium carbonate. So if you think about it, every time this happens, it's carbon dioxide that's taken out of the atmosphere and put into rocks. And I know we're in the category now of super boring, but at the same time, like, this is a really kind of interesting part of the carbon dioxide exchange that we don't think about that much. Because we think about the ocean, we think about the air, we think about the breathing out and the photosynthesis and should we plant trees and all that sort of stuff. But what people don't think about all that much is that carbon dioxide is literally removed from the atmosphere on a more or less, I don't want to say permanent, because but we're talking about like millions and millions and millions of years. Once you get into the calcium carbonate, do you know how it gets back out? That's the only way, right? The only way for this to get back out is a volcano. right? And so this, you know, I don't even know what would happen if I tried to draw a picture of that process, right? But eventually, the rock cycle, which you studied in earth science, the rock cycle, you know, brings, you know, through earth-moving processes, will bring this into contact with deeper parts of the earth. The calcium carbonate melts. That's magma. Magma is melted calcium carbonate. Limestone, by the way, is what calcium carbonate is. Sorry, limestone. Should have mentioned that, huh? Yeah. Anyway, limestone. Let's write it as if you were going to read it. Limestone. And so that's the only thing in green. And so that is what becomes magma, and that is what goes back up into the atmosphere. But once again, it's roughly imbalanced because, I don't know if you remember, I always point to the board that I was on like a week ago when I was talking about volcanoes. That turns out to be about, so hold on, let me draw a volcano. Okay, we got it. 0.1 gigatons per year.
Are released
by volcanoes, and 0.1 gigatons a year absorbed from the atmosphere. And so, okay, now I know that this seems super boring, but the last thing I want to say about this, for me, was just blew my mind. Where do I put it? Okay, tell you what, take a minute and get this, because I need to erase some
Wait,
stuff.
I thought you said it was imbalanced, but it is balanced because it's 0.1.
It is in balance, not imbalanced. In
Oh.
in balance. Yeah, sorry, I mumbled.
I have a question about the sand. So I thought that like sand was just like small rocks. So how is it that sand has that specific?
Sand. Well, okay. There's dirt, and then there's sand. Sand is a specific substance, actually. Sand is silicon dioxide, and that is what can be turned into glass. And in dirt, there's so many other things. There's like little, you know, little, what are they called? Like foraminifera, like tiny little creatures and pieces of broken down organic matter and crushed up bits of other kinds of rock. But sand is just silicon dioxide. Okay, so the last bit I'm going to tell you right now, and well, I would tell you two other things, but I sort of, I want to tell you one thing that I thought was super cool. Continental movement, right? Movement of continents. You know about this, right? Continents. Our continents sit on tectonic plates, right? They move around, and hopefully we know this. They float on islands of or float on oceans of magma, and they move, I don't know, centimeters per year. Continents move about as fast as your fingernails grow. Is about the speed that continents move at, and so you know it isn't much. It's you know that much per year, something like that, a centimeter or two, but it adds up over time, and it causes our mountains, it causes you know, earthquakes, the volcanoes, and all that sort of thing. But here's one. Okay, here, earth science people, what do you call it when two plates collide? I mean, there's three things that can happen, right? Isn't there?
Subduction.
Subduction is when one goes under the other. Is that right? And then that's when one takes the other, and you're my continent now. Okay. Anyway, mountains can build up, right? This is, you know, continents crash into each other, and the force of that crash can build up mountains. Shut up. What's so funny about my mountain? Hateful, terrible people you are. So these are here's something, this is actually something really interesting. These are the Himalayas. By the way, the Himalayas, tallest mountain in the world. How old are they? What's that? Young. As mountains go, they're pretty young. Yeah, does anybody know, approximately? I only learned yesterday.
Wait,
I'm
I really
Aren't they
lording my
younger
knowledge of
than
how old the
the
Himalayas are
mountains
over
that
you.
we live on? Huh?
Yeah.
They're younger than we live on. Were our mountains once that tall?
Yeah,
Before they were, that's cool.
Yeah, the Green Mountains, Appalachians were sort of a continuation of the Appalachians. Yeah, they're definitely older. The Smoky Mountains in Tennessee, much older. They're rounded off, but anyway, about 40 million years, which seems like a long time ago, but honestly, 40 million years in terms of like 4.5 billion years, not very long. And so this is the thing though. So 40 million years. The Himalayas formed, and they exposed a tremendous expanse of silicate rock. And as it turns out, this is one of the largest drivers of our climate over the last 40 million years. That the Earth, that this has been drawing because it did two things. One is it changed the sort of the wind patterns. That's the wind.
What's the rock named again?
Silicate rock.
Okay.
It changed the wind patterns, and it also built a huge rain pattern. Because of the height of the mountains, because of the way they interact with the atmosphere, they actually change the way that the weather happens in that part of the world and cause tremendous precipitation to fall on these mountains. And so that has been taking CO2 out of the atmosphere at an increased rate because of these. So the formation of this mountain range has caused a general cooling trend in the atmosphere for about 40 million years that we're actually moving opposite to now with what we're doing with climate. I guess you could see that, you know, in times where, for example, volcanism is higher, there were times in Earth's history where volcanoes did significantly increase the temperature of the Earth, right? And like, you know, right now it's in balance. That doesn't mean it's always been in balance. There's, you know, there's times when there's much more volcanic activity, and that is going to increase the atmospheric carbon dioxide, and that is going to increase the temperature. Temperatures have been much higher on Earth than they are now, with the caveat that never this fast, or never over this short of a period of time. But all right.
So since they're in balance, that's like another reason why they could cause
All aboard.
What? I didn't hear anything.
That makes me suspicious of you. I hate you people so
I bet
much.
it's just someone like messing with the intercom that accidentally.
That wasn't in here, was it?
it was
It's up there, yeah.
Choo choo, Mr. Perrin.
It's gonna happen again. Mr. Adrock, can you access the intercom for like classroom?
If I could, I would be fired by now. Nobody would ever. I've asked.
That's what.
I've asked, hey, how do we access the intercom from our phones? Perrin said, yeah, from my cold dead hands. Will you get that secret?
What, have you ever heard that noise before? 'Cause
I've been in this room for 13 years and I've never heard that noise before.